All right, we'll go ahead and get started. Hello again, and thank you for joining us. I am Jasmine Navarez, Digital Content Coordinator here at Simulations Plus. I'll be hosting today's webinar behind the scenes, making sure we don't have any technical difficulties. In this webinar, Robert Fraczkiewicz, Research Fellow, will discuss the fundamentals of ionization and ionization modeling and demonstrate some features of the new pKa model in Advent Predictor 11. Eric Jamoy, Senior Director of Business Development, will serve as our moderator today. A few housekeeping items before we begin. We take your privacy rights seriously. By registering for and attending this event or participating in the Q&A session, you're allowing us to contact you for follow-up. You may ask questions via the questions panel on your dashboard at any time. If you need assistance, please use the hand raise icon. We'll address all questions in the Q&A after the presentation. And I'll pass it off to you, Eric.
All right. Well, thank you, Jasmine. Thank you for all of you for joining us. It's my pleasure to introduce our presenter for today. Robert Fraczkiewicz is a research fellow at Simulations Plus. He has been at Simulations Plus since 1998. That's over 24 years. It's a pretty impressive track record. Robert has been at the origin of the pKa model development since the very beginning. As you know, our pKa model is not a simple statistical model. There are many steps that are necessary in the assembly of this model, and Robert is going to help us grasp how that is done. He has also coded some of the most impressive algorithms that we've packaged in our software, including the HTPK approach in a net predictor. And so without further ado, Robert, the floor is yours.
Thank you very much, Eric. Can you hear me?
Yes, well, absolutely. Okay.
I'm going to save the bandwidth. Hello, everybody. I'll just wave here and stop the video. Better do that because I'm speaking from my home. Fundamentals of multiprotic ionization and ionization modeling. In order to build a successful model of ionization, especially with regards to multiprotic compounds, one has to understand how ionization works. And the poll that just flashed on the screen was very interesting. About 20% of you know the fundamentals or the microscopic theory of ionization very well. So they will be bored probably. But for those who just know a little bit or not at all, I think this should be interesting because first of all, let me get the next slide. Just like Luke Skywalker, who went to planet Dagobah to train with Master Jedi Yoda, he wasn't progressing, unfortunately. His baggage of misconceptions was hindering him. And finally, Yoda says, well, you must unlearn what you have learned. Okay? I don't know. No different. Only different in your mind. You must unlearn what you have learned. This was the worst imitation of Yoda I've ever heard. So anyway, there is a baggage of misconceptions, and I call them myths. Clearing up myths about aqueous ionization drugs. Okay? The first myth, which is very, very prevalent, is that apparent pKa are measured in the traditional titration experiment. There is a prevalent belief that every apparent pKa can always be assigned, so-called assigned to a functional group. Therefore, if you have a molecular structure, you have your compound and measured pKa's, the first instinct is to affix the measured values to individual functional groups. Okay, let's talk about it. Here is a very simpler example. glutaric acid has measured pKa of 542 and 435. And one popular program, actually many popular softwares, report predictions in the following way. They affix predicted numbers to each carboxyl groups, to each of the two carboxyl groups. And you can map measured values the same way, right? You can put here and there, but that should give you a lot of thought, especially if you're on the skeptical side. So move your, use your scientific mind and think about it a little bit, right? What is wrong with this picture? The molecule is perfectly symmetric. Okay, so each carboxyl group is equivalent to the other one. Why would they have different properties? By the same token, here's another example, which is a bit more advanced. Mellitic acid. It's a benzene ring with 6 carboxylic groups. Each of the 6 apparent pKs was dutifully measured by those authors in 1935. They differ by over 5 orders of magnitude. Okay? There are over 100 ways of trying to assign each apparent pK to individual functional groups. Which one is correct? That's the baggage of misconceptions you have to deal with if you still think that apparent pK should be assigned. This is the prevalent belief. That's how polyprotic molecules protonate. If you start with fully deprotonated acid and start lowering pH, adding protons, and in other words, the thinking is that the first proton attaches to one group and the second to the other group. That's not what happens, though. This is the true picture. There's a 50% chance that the first proton will attach to either group. Okay? They're perfectly symmetric, so the chances are equal. So you have population. If you isotopically label one of the oxygens, okay, you will see a population of 50% of this species and 50% of this species. And of course, after adding the next proton, they collapse to a fully protonated form. Don't think that this is just a property of symmetric molecules. It's not. Every compound protonates like that. You have a statistical distribution of what we call the microstates. I will talk about it in a moment. If you break symmetry with a methyl group, for example, you will have a slightly different distribution from perfectly 50-50. We'll have slightly more of these microstates and less of these ones. So that's the true picture of multiprotic ionization. Overall, you have a simple mathematical problem of having n ionizable sites, and at certain pH values, k protons that distribute among those sites, resulting in n choose k distinct combinations. Let me give you an example of n equal 3. We have this simple illustration of deprotonated sites as empty circles and protonated sites as full circles. So starting with 0 protons, you have 1 microstate, okay? 1 proton can go 3 different ways to 3 sites. 2 protons the same way, 3 different ways among 3 sites, and finally 1 fully protonated species. So knowing that there are K protons somewhere is also called a macrostate. A macrostate, macroscopic state, and also apparent pKa is also called a macroscopic pKa. So apparent pKa actually corresponds to to only limited knowledge. Okay, knowing that there are K protons somewhere, knowing where the K protons exactly are is in the realm of microstates. Here's a concrete example. There is a cetirizine that I flashed on the one of the first slides. These are all measured microstates. Okay? These are not predicted by any software. These were measured by a very impressive work done in 2009. We start with fully deprotonated state, and the first proton attaches almost exclusively to this tertiary nitrogen. It's 91.1% prevalent. The other microstate is only available at 0.9%, where the other nitrogen gets protonated. And finally, the really poorly populated microstate with hydroxyl group protonated is 0.02%. So you would be actually justified by assigning the first microscopic pKa to this microstate or this functional group, but you wouldn't be for the next two, because the population of microstates is non-negligible. You have about 65% of this one and 34% of this one and only 1.2% of this one. So you cannot say that the ionization transition between these two is due to a single functional group. It's not. Essentially, all groups participate. Here's a more detailed picture. All the microscopic transitions have their own microscopic pKa, okay, micro constant, which was also measured by these authors, and they are depicted right here in the picture. Okay, there are 12 micro constants, and they determine the relative distribution of microstates. So distribution microstates per macrostate, let me put it that way. They have to add up to 100%. And finally, the observed apparent pKa's are macro constants. They correspond to transitions between macrostates. Curiously, if you wondered about malitic acid, it has 64 microstates in total. And as highly symmetric molecules, it, of course, it's quite apparent that they are equally distributed if they represent the same symmetric equivalent species. So coming back to what I said, accurate, thermodynamically accurate view of ionization is as follows. All groups participate in transitions between different macrostates. Carboxyl group, this nitrogen, all of them participate. And you can form an apparent expression for the Ka, right, the ionization constant, by taking the whole population of microstates and their concentrations. Okay, they are the molar concentrations of this microstate, this one, and this one, and dividing them by the whole population of other microstates. So that's how the pKa works. It's a function of not a single group, it's a function of all groups in the compound. Myth number two is also very prevalent. It's so even more ingrained than the myth about assigning pKs. The myth number 2 is that every apparent pK can be unambiguously labeled as either acidic or basic every time. Well, it's only valid in limited number of cases. Okay, when you have monoprotic compound, yes, of course, you have unambiguous acid and base. Or if you have a compound with only acidic and only basic groups, yes, that's also accurate. But for compounds with mixed groups, it's less apparent. Let me tell you why this myth is so prevalent. Normally, if you look at macroscopic transitions between, let's just talk about this very simple molecule which can either lose proton or add proton, so it has an acidic and basic group. When you have a proton loss, then according to a physical chemist point of view, you have an acid. Because physical chemist focuses on the whole molecule and its charge states. So the physical chemist point of view is macroscopic. By the same token, if you gain a proton, okay, you go from HM to H2M plus, you have a base. It's simple, unambiguous, and accurate. Moreover, experimental properties, and I've just put their solubility profile as a function of pH, follow that point of view. Okay, on the low side, you have hydrochloride salt, and that corresponds to base. Again, on the high side, you have sodium salt, and that corresponds to an acid and free base in between. It's easy and simple. Unfortunately, most chemists subscribe to an organic chemist point of view. They pay attention to individual functional groups. And that ties to myth number 1 about assignments as well. So this is a molecule. It's an amino acid. It's a Zwitter ionic molecule. So instead of looking at global charge states, macroscopic charge states, they look at the individual functional groups and they say, oh, no. Okay, the proton here is attached to amine. It must be a base. So don't call it an acid. So that, boom, okay, you cross acid and put base. On the other hand, the proton comes off the carboxyl group, so it must be an acid. So it's completely reversed. It's complicated because you mix macroscopic pK with microscopic states. You see what I mean? And that mixture leads to a lot of problems. And this has been, a very poorly defined definition or a very poorly defined concept of acids and bases that are based on just individual microscopic states instead of macroscopic. If you look at cetirizine, for example, you have almost pure base for the first transition. Yes, I give you that. That is the summation of these microstates. But if you sum proper microstates for the other 2 transitions, it's not so obvious. Okay, you have only 66% acid, 34% base, and vice versa. Okay, it reverses for the last transition. So again, this is not predicted. Okay, it all has been measured. Also measured from a poster. I stole the data from a poster at LogP Symposium in 2009 for morphine. By the same token, you cannot have a pure acidic or basic transition. They're mixed. If they're mixed to the extreme, like tyramine, Then you have what we call mixed PK, and in our program, we have a separate column for those cases. Okay? In here, you have 51% acid, 40% base, and vice versa, right here. So that I'm 2 minutes above time, so I'm stopping here and taking questions. Thank you very much.
Well, I don't see any questions in the Q&A pane, Robert, and sometimes they go in the chat, but there's none in the chat either. So I think you can. Oh, there was one. What is the criteria for assigning a mixed pKa?
Very good question. There is an algorithm that was created by Bob Clark, who worked for us for a while. We are calculating the percentage of acidic and basic transition. Just to make it simple, we're calculating the population average percent of acidic and basic, and we subtract one from the other. If it's close to 0, like in this case, then we assign it as mix. And we have hard limit of 0.15, plus and minus 0.15. In this bracket, we have mixed cases, and outside the bracket, we have acidic or basic. Again, this is all based on the unfortunate organic chemist point of view. It leads to a lot of confusion and misleading conclusions. So it's much better to simply use ADMET predictor in a visual way. It's much better to simply look at all microstates. Program displays it in such a way that you can understand what's going on. Okay.
Yeah. I think there's another question popped in the chat is, that what's most important is what is at pH 7, but I mean, in reality, probably not true, because I mean the difference in pH environment between a gastric compartment and what you have at physiological 7.4 is very different. So you probably want to see actually a pretty significant spectrum of what happens. Physiological pH has actually quite a range, right? Depending on where you look. Yeah.
Stomach has pH of 1.2 on average, so it's quite important to know what's going on there.
Indeed. All right. So did you want to continue then? I think we're pretty good with questions. I'm sure more will come.
You're absolutely right. It's time for another presentation. So let me open it and share it in a moment. Okay. So the next presentation, and I will share it in just 1 second. And the next presentation is about our model. Share screen. Let me know if you see the screen.
Yeah, you're fine, Robert.
See the screen? Okay.
Yep.
Good. Very good. I will put it in slideshow mode.
Actually, We
Can you
just
see
see
the
your
screen?
name. We just see your name. We don't see your we don't see your screen right now.
That's strange.
Yeah.
Very strange.
Yeah.
How about
Now
now?
you're good. Now you're fine.
Ah.
Yep. Yep.
All right. So yes, we have released Admet Predictor 11 this year, and it has a new PK model. But in order to understand it, it's good to actually go back to 2012. In 2012, we already had a model that was trained on about 11,000 compounds taken from published literature. And this model was labeled as version 6. I use this way labeling because it's in the paper that we have published. So in order to understand tables, we'll use that as version 6 as model trained on public compounds only. In 2012, Bayer Pharmaceuticals had shared with us an additional set of about 16,000 compounds with measured pKa. We retrained the model with the combined data sets, and that resulted in version 7. We've published the description of the model and the results in 2005 in Journal of Chemical Information and Modeling. Here's the reference if you want to see. By the way, we always pay for open access, so you don't have to subscribe to the journal. All our papers are open to everybody. By the way, the meeting is recorded, so you will be able to see the slide again if you missed the reference. Version 7, as you know, as predicted, has shown dramatic improvements in quality of the results when evaluated in both public and Bayer chemical space. But in particular, of particular interest to Bayer, of course, was evaluation on compounds that were never seen by the model. And they compiled 3 test sets, 1, 2, 3, with varying number of compounds and varying degree of similarity to what they call industrial set. This was a set that was included in our training, in our model training. Okay. So the first set was most similar. There's like 98% compounds had Tanimoto score above 0.8. And the RMSE for this set dropped from 1 in version 6 to 0.58 in version 7. And similarly, set number 2 was less similar. It was the set of I think strongest acidic and strongest basic pKa. This was also favorable in terms of the results. The RMSE dropped by 0.3. And finally, the last set, curiously, the least similar one, actually fared slightly better than the previous one. But still, the version 6, version 7 RMSE drop was also 1.3 log units, was dramatic improvement. The model also compared favorably to, well, it's an unfair comparison, as you can say. The Bayer scientists extracted a set of 1,000 compounds from the third set, from the 12,551 set, and ran it through both programs, Admet Predictor version 6 and ACD Perceptor version 12. ACD Perceptor could not process 19 compounds, so the numbers reduced to 981. The statistics were similar. Okay? It was really, head to head. But of course, version 7 has improve dramatically over this. So that was then, and for 10 years, I think Bayer was happy with the model because we haven't heard too many complaints, other than requests to change the software in terms of structure handling. But we hit the pay dirt last year. 3 new industrial partners, Roche, Genentech, and Bayer Crop Science, have also indicated inadequate coverage of their chemical space by the version 7 model. They followed Bayer Pharma example, and they shared with us significant amount of experimental data extracted from their corporate databases. About 19,000 compounds from Roche. Genentech provided 2,400 compounds, and Bayer Crop Science has provided 4,100 compounds. So we were very busy, for the period from August to March, rebuilding the model with the combined data sets. And of course, the number of compounds does not translate directly to number of ionization constants. There are multiple constants per compound. So the total number of ionization constants over 70,000. I will carry the label. I will label the new model by version 11 to distinguish it from the previous ones. When you plot the resulting data sets, on the first 3 components of unmultiplicator molecular matrix, you have a projection of multi-dimensional space into 3 dimensions. But you can immediately see differences, especially between industrial and public data sets. The public is in blue, and the industrial data sets are in red, yellow, and 2 shades of green. There are some unique pockets of compounds that are very unique to public space, like on this end, and so on. And also unique pockets that are characteristic to each of the other data sets. This is quite involving to look at all these over 50,000 points on this graph. So I separated them, and you can see them how they look like viewing from above, from the 3rd axis. You can see how they look on this graph. But of course, keeping in mind that this is a very primitive projection. It's akin to the Plato's The Cave allegory. It's a gruesome allegory in which there are slaves that were from birth. They're changed to the cave. They can perceive the external world only by looking at shadows on the wall. They never see the world how it really looks like. They can see it only by looking at shadows on the wall. And of course, they form a lot of misrepresentations and misconceptions due to that. So by the same token, looking at the principal component projections, you also just look at the shadows. Version 7, version 11 performance, and comparatively, it's apples on oranges because there are different number of compounds, of course. This is the original model as it was trained on over 25,000 compounds and internally tested. This test set was never involved in the training algorithm of 8,000 compounds. So the RMSE values are comparative. It's slightly better in version 11, also on the test set. So we're happy. But the real test comes on looking at the industrial data sets. So first 3 slides are on about the data that was shared with us. Version 7 versus 11 versus received data. So model 7 predicted Roche data set with 0.8 RMSE. Okay, and you can see this cloud of points is scattered a little bit. And of course, after including this test, partially including this test in training and internal testing, it improved to 0.415. The data set shared by Genentech, 2,400 compounds, same deal. The RMSE improved at about 0.3 after using it in model building. And finally, Bayer Crop Science, improved quite a lot. Okay, this was the most challenging set. Not surprisingly, okay, agrochemicals sometimes they overlap with pharmaceuticals in terms of chemistry, but sometimes not. Sometimes they're distinctly different. Eric will talk about it one of these days on agrochemicals versus pharmaceuticals. So stay tuned. Improvement was dramatic, 1.1 to 0.55. Now, we send the model to each participant to have them test the performance on external data sets that were not received by us, were never seen by us. And Roche did that at their site. It was a set of almost 3,000 compounds. Version 7.9, version 11.68. Okay, good improvement. Genentech, also around 3,000 compounds. Improvement was not as dramatic, 0.2 log units, because even though there is a cloud of points that hugs the identity line, right? There's still a lot of compounds that are, all of points that are stubborn outliers. I'll talk about it in a moment. And Bayer Crop Science, a very nice improvement from 1.1. This was an external test set of 167 compounds, improved from 1.1 to 0.76. One more thing, if you are familiar with sample 6 competition, we participated in that competition in 2018. It was a contest of predictive software that for ionization constants, of course. And we came second after full quantum chemical calculation of the energies and so on. We came second on a test set that was, of course, synthesized after the reception of the results and evaluated after the predictions were made. Measurements were, of course, performed for the 24 compounds, and the statistics was calculated, and we came number 2 in terms of RMSE. Again, that was version 7 of the model. And I have these 24 compounds, of course. So version 7, again, 0.73, and version 11 improves that quality of prediction to 0.57. Right? So the conclusions of this exercise is that the chemical space has been significantly expanded, and prediction accuracy has been improved quite a lot. Of course, Roche reaped most of the benefits because they shared the biggest data set. Also, yeah, I will not talk about tautomers. I don't have, unfortunately, time, but there's another fascinating topics. But they figure out that changing input tautomer for some biggest outliers improved predictions. So that was good. Genentech delivered much less data, and I'm not sure how much it is similar to their external tests. I don't have that information. It would be nice to know. So now Bayer Crop Scientific an intermediate amount of data, but also the improvements in prediction quality were the most impressive, okay, by about half a log unit. Now, on the significant, it's misspelled, significant stubborn outliers. We've seen it all, okay? There's no database is free of errors, and we completely understand that. So what were the outliers? Well, purely neutral compounds containing no ionizable groups, but with measured pK. So that was a mystery that I still don't know how it happened. It's probably database error, right? So misrecording or something like that. Compounds with more pK values than the number of ionizable groups. That's the same, is in the same bucket as compounds with pK but no ionization at all. pK values just don't make any sense. Like carboxylic acid with pK of around 10. I don't see any interaction that would raise carboxylic acid pK by 6 log units to 10. Makes no sense, especially if there are no exotic groups nearby. Just normal molecule, but it doesn't make sense. And finally, pKa cliffs. Okay? Values vastly different from those of very similar compounds. Those similar compounds are predicted very well, and suddenly there's one that has completely different pK for no clear chemical mechanism for this. So I have three hypotheses of why those outliers come up. And the first one is the following. Okay? The popular instrument for measuring pK, the Sirius T3 instrument, has a software, of course, that lets a user handle the results. Here's a parameter. Okay? Number of visible pKs, and visible means visible in the range of the instrument, that is between 2 and 12. Okay, that's the range of the fast mode of measuring pKs with this instrument, between 2 and 12. So this parameter is usually predicted by the instrumentation software, but it also leaves a user an option to specify it manually. So the user is guessing, right? The user is guessing. There will be, for example, in this example, that there will be 3 pKs in the 2 to 12 range. But if the guess is wrong, okay, there are still 3 adjustable parameters that the software feeds to the experimental point, and one of them is completely bogus. You see what I mean? This over-parameterized, and instead of 2, you have 3 pKs. Of course, there are different values, and one of them is completely bogus. That's one mechanism. Another mechanism came up actually this year in a very impressive work. The team of Professor Verbich has studied aggregation of clofazimine. And they were not happy with the reported pKs in the literature for this compound. The pK differed by 3 orders of magnitude. There are different results from different groups, different methods, and so on. It turned out that if you neglect aggregation, you get bogus results. If you include aggregation explicitly, you get true pKa. And the true pKa is, let me go back. Yeah, right here. It's measured at about 9.5. So it's higher than any of the previously measured results. Okay. So if you explicitly filter out the effect of compost dimerization, and Professor Verbich will be on day 4 of this conference. She will talk about it. Okay, so please stay tuned. Okay, and or read the paper if you're interested. How to do it, how to explicitly filter out dimerization. But you see, the part of this filtering is a principal component analysis of the absorbance matrix. What the algorithm does is calculates principal components from eigenvalues of the squared matrix. And from those components, they can figure out the number of independent light absorbing species. All right. If someone confuses a dimer for a doubly protonated microstate, that can result in a false second pKa. And Professor Verbich actually communicated to me that in her first analysis, she committed that mistake and led to the first pK of 9.1, which was actually very close to one of the previously reported values, close to the true value as well. And the second pK of 6.5, which had no reflection in reality. It's because there are 3 independent light absorbing species, okay? The neutral form, singly protonated form, and, well, dimer, right? But if confused for the doubly protonated form, well, that results in a bogus pKa. And of course, again, stay tuned. Day 4 on November 14, right? November 14, you will hear from the professor directly. And finally, I attended a webinar that was delivered by Rebecca Ruiz on June 15. Very nice talk. The underappreciated effect of decomposition. How bogus pKs can result from neglecting decomposition of compounds like quercetin and amphicetin. She will also talk on day 4, right? Following Professor Verbich's talk. You will hear from Rebecca Ruiz on that topic. So, again, decomposition, if neglected, results in bogus results. That's it. That concludes my talk, and I will be happy to take questions.
Oh, well, thank you, Robert. Very, very interesting, very interesting work, and I think a lot of people have had some comments about how impressive the improvement is, by just increasing the size and of the training set, and also the coverage in terms of chemistry space. There was one question that came on the sample 6. I think I know. I just want to make sure I got it right. That I don't believe any of the sample 6 compounds that we predicted were included in the version 11 training set.
No, they were not.
Yeah, no, because I mean, that's one of the things we try to do, is to keep enough external test sets that we can unambiguously compare from, one version to the other. I mean, otherwise, if, these compounds obviously were not in version 7, but then they would be in version 11, then in essence, I mean, if we looked at the improved predictions, would be comparing, apples to oranges. So, for that reason, because then they would be external to one model and then internal to the other. So then, how could you, you know, legitimately compare one to the other.
Oh, absolutely. You know, I keep a whole number of external test sets, small test sets that I never include in model training. They're indispensable in model evaluation.
Yeah.
You see, it's some of them are just literature compounds. Some of them are industrial. They're also published in some Vertex published their data and so on. So yeah, I keep those compounds.
Yeah, and you know, and if I can comment, I mean, some of the aspects of that improvements, I mean, are, you know, really impressive, because I mean, one line of thinking could say, well, you know, if you already had 26,000 compounds almost in a training set, you've already sampled a lot of chemistry, you've already seen a lot of things. How much more is there really to learn in terms of, you know, capturing, you know, subtle chemistry variations? And well, the answer is, well, there's still a lot to learn. You know, I mean, that's the other challenge, I think of what we do. And I was going to ask you, you know, the most challenging part, you know, one being that we really don't know upfront how much the model is going to improve before we do the work. I mean, we have to do the work of data curation and, you know, everything else before we can even find out if the model is going to improve. And we don't really have the answer until the end, but I'll let you maybe comment on the sort of the challenging aspect of the model construction.
Oh, yes. Absolutely. But, you know, in the interest of time, we still have 7 minutes. Could we start answering questions?
Yeah, sure. I'm taking them a little bit randomly, but does the PK model account for the self-association of a drug substance?
So, no, it does not. So aggregation, again, the PK model has no way of knowing whether the compound aggregates or not. That's a subject of a separate experiment. That's a subject of having enough data to predict whether a compound aggregates or not. So no, there's no mechanism for that. It assumes that the presented compounds are in monomeric form.
Okay. And another one, which is a somewhat different topic, is there a way to predict the impact of pKa of excipients and the drug in the formulation mix?
Impact of pKa, impact of ionization of excipients.
Ionization, I think, yeah.
Oh, yes, absolutely. We have a number of other software offerings, Gastro Plus, DDD Plus, Membrane Plus. The first one is for simulating the fate of a drug and excipients as well in a living organism, especially in the intestines and also in the bloodstream. That takes ionization of not only drug by excipients into account as well. The DDD plus is particularly useful in that respect. It's a simulation of the dissolution experiment. If you measure dissolution in, let's say, an apparatus, a paddle apparatus, it's good to know the resulting pH. And the compounds, such as drugs, excipients, and so on, will affect pH, even if you have a buffer. Remember, right? You're dealing with saturated solutions, which, you know, not always, okay, but usually mean concentrated compounds that are ionizing, and buffer capacity may be easily exceeded in those cases.
All right, good. No, thank you. I think we still have a little bit of time, so I'm just going to keep going through the through the questions in the panel. Are the pK values used to well, or ionization again in this case, are used to predict permeability in the gut?
Oh yeah, absolutely. GastroPlus does have a model which is based on log D versus pH profile, which is predicted by administrator, by the way. And from that model, it calculates permeability in every compartment of the intestine, including colon and cecum. So yes, it's very important in terms of calculating permeability.
Another one is, how do we use microconstants log D pH measurements? Well, I think log D versus pH measurements. How about log P apparent versus pH, log S versus pH?
Hi, Alex. How are you? So how do you use it in measurement? Gee, you're asking the wrong guy. I'm a computational chemist. No, not much about measurements, but let me talk about predicting log D profiles, log permeability profiles as a function of pH. It's in principle, yeah, they could be resolved microscopically, and you could have individual partition coefficients and individual permeabilities for every microstate. But in my humble opinion, it's not needed. Okay. The macroscopic view of both log D and permeability is sufficient to make other predictions. So it would be a monumental task to collect enough data to predict these profiles microscopically, but it's not needed. If you have a different opinion, Alex, let me know. But I think that macroscopic view of both not only log D and permeability, but also solubility is sufficient.
Okay.
Okay.
Excellent, Robert. I think we're really coming up on the hour here. I think we'll probably just let Jasmine close the session.
Sure. Thank you, Robert. Thank you, Eric. Thank you all. For any questions that we were unable to answer, our BD team will reach out to you with answers following the webinar. We invite you to visit our website to learn more. I put a couple links in the chat that you guys can visit. Make sure to join us for the upcoming session in the Ionization Prediction Summit webinar series on October 31st. This webinar has been recorded for playback and will be available on our website and YouTube. This concludes our webinar for today. Thank you, everyone.
Thank you. Have a great rest of the day.